Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, and good morning to our research talks in the new building 99 that we just moved in a week ago. So this is actually the first talk that I'm hosting here, and I'm very grateful to be able to host Ngan Chin, who is coming from Singapore University. And we have actually a little bit history together because I looked into his earlier work on size types. Then we both moved on into verification, and he will talk a little bit about verification of heap properties using his work on separation logic. Welcome, and
Thank you. So this piece of work is joint work with my two students, Puhai and Christina, and also my collaborator at Durham, Sen Chao. So it's a work that we started about 2 years ago doing automated verification using separation logic. So basically the goal of this work is to try to handle mutable data structures with sophisticated invariants in as precise a way as possible. And then we also want to capture various properties about this kind of data structures like length, height, maybe back properties. And then here the challenge we face here looking into it is first we want to be able to perform strong updates in tracking the properties of these data structures in the presence of aliasing. And also we want the facility to be as flexible as possible, allowing user to define predicates about their data structure. And our emphasis is as much as possible on a practical tool for verification. And here, as I was mentioning, we rely on what has been done before in the area of separation logic. Let me just give a very brief background first about separation logic. I guess most of you in the audience may have some knowledge, so I'll be very quick with just 2 slides. Firstly, separation logic is an extension of Hoare logic that will allow us to reason about mutable data structures. And foundations for this work has been done by Peter O'Hearn Reynolds and their collaborators around about 7 years ago. So those were the foundation papers. And essentially, the extension of separation logic allow you to have 2 main connective. One is called spatial conjunction, which allows you to describe 2 formulas about disjoint heap. And then the other thing is spatial implication that allows you to, if you augment your current heap with some additional heap structure, you should be able to assert things from there. And this spatial implication is quite useful, especially if you are wanting to reason backwards in your programs. So as we are mainly focusing on forward analysis here, we'll be mainly using in this work spatial conjunction operator. So just a quick example about the separation formula as it was introduced by Reynolds in the Leaks 2002 paper. Here is a formula that says that you have a variable x pointing to a memory location, 2 pieces of consecutive memory location containing the value 3 and y. So that's just the points 2 formula. And over here is the representation in the actual heap where x is pointing to these 2 memory locations with contents 3 and y. And if you use the spatial conjunction operator and write 2 formulas there, then what you are essentially capturing is the first formula is to capture this part, and then the second formula is to capture a disjoint heap. And because this content here is the same as y and this content here is the same as x, you get a cyclic structure built that way. But if you did not want to use the spatial conjunction, but instead you use just the normal conjunction, then what you may effectively mean is you would like these two pieces of formula to apply to the same heap. So that could mean just a simpler structure that is cyclic and also alias to each other. So our approach in this work, I'll just give a very brief outline, and then after that talk to you about the main techniques that we have, how to verify, how to do proving of separation formulas and approximation, and then later on how we improve the expressivity of our system. So our work here mainly is focused on capturing properties of data structures and also on the invariance of data structures, allowing us to express things like height balance, sortedness in the data structure and then tracking them. And to do that, we allow users to define their own predicates about data structures, and in particular we allow these predicates to be inductive or recursive in nature so that it can express interesting things. And one of the key part in our system is a sound entailment prover for separation logic, which we have implemented and which we have also extended with various features to make it more expressive. And here we are not going for completeness in our proving. We are just going for soundness and then perhaps adding on techniques that will make it as expressive as possible. In a nutshell, our system really contains two parts. I guess most verification systems will contain these two parts. Firstly, there is the code verifier part that takes the code and then generate various proof obligation. And then secondly, an entailment prover that will allow us to reason about those proof obligations. The difference here, since we are based on separation logic, is our entailment prover must be able to handle separation formulas. And we expect the users, of course, to provide their own code and also pre-post specification for both methods and loops. And then if you are describing certain data structures, you are expected to also write predicates about those data structures. And lastly, to make it expressive, we allow users to write lemmas about these predicates. Maybe there's a relationship between one predicate and another. The user can provide that lemma linking this predicate together. And then our system will automatically prove that lemma and also apply that lemma where possible or where needed. So just a bit of example on some of the data structures that can be expressed using separation formula. Firstly, here is just a singly linked list data structure in which you have a root pointer pointing to the beginning of this linked list, and then towards the end of the linked list there's a null reference. So you have a null terminated linked list, and we can capture this by this predicate here, LL, together with a parameter that indicate the length of this linked list. And to express this, you really need two cases. You need the base case that say if the root pointer is null, then the linked list is of 0 length. Or if the root pointer is pointing to a node, that means it's non-null. Then you also expect to have a separate component here, which is the rest of the linked list that is referenced from this next field here. And then the rest of the linked list will have length n-1. So that's the definition of that predicate. And we expect here a root parameter by default, which is the initial pointer to your data structure. And then the other thing that we allow the user supply in order to make the predicate more informative is some pure invariant that we expect to hold for the parameters of the predicate. So in this case, we expect that the list to be non-empty, to be of a positive length 0 or more. So this invariant will be supplied by the user, and our system will check that this predicate in fact will satisfy this invariant. Let's look at a slightly different data structure, this time a little bit more complex with more properties. In particular, we expect this list to be now sorted, and we expect this list to be non-empty. Okay, and the kind of properties we may be tracking for this data structure are firstly the length, the minimum and maximum value of this sorted list. And we have two cases. One is just a singleton node. So this is a singleton node where it's now terminated. And then here we expect the value itself to be minimum and also maximum. and the length to be 1. So this is user specified. And then in the recursive case, the first node will contain the minimum value, but the rest of the sorted list will contain the value k, which is just an extension value, and also capture the maximum value in the rest of the linked list. And then in order for this linked list to be sorted, we have this property attached here. This is kind of invariant about this data structure that we capture, that the minimum value will be less than the next value k. So that's expected in the sorted linked list. And then the pure invariant that is true about this predicate is just this is not null, and also min is less than or equal to max. So we expect this to describe a sorted list. It just to describe the minimum, maximum, and then the length of the sorted list. And also it's non-empty. Another example, so instead of just,
Can I ask a question?
Sure.
In the single linked list example, what would change if you would just use a normal conjunction there? So how would that change the
if you use a normal conjunction in the intuitionistic separation logic framework, then this node may in fact alias with the rest of the linked list.
It has to be alias.
Not has to be, may alias. Yeah. If you depending on whether you are saying is classical separation logic or intuitionistic separation logic. So if it is intuitionistic, it means it may alias because the heaps may overlap. But in this case, if you use a separation conjunction, it means it's completely disjoint. So you know they are not going to alias.
But since you have the length explicit there anyway, that makes sure that you don't have cycles, right? Otherwise the length would be infinite.
You could be defining something that is false. So that's something that you may end up with if you're not careful.
Okay.
Can you remind me again what the AR is standing for?
So this is the content of the first value and the next field. Usually the node contains two fields. One is a value, the other is the next field. So A is the content and then R is the pointer to the next field. So I didn't give the definition. I just assumed this is something that people may have encountered before. Okay.
So, and if you introduce new variables, they are all existentially quantified, like the k in below there, or where?
Yeah, I mean, you could explicitly write extension quantification. In our system, whenever something is free that is not bound to this parameter, it will be considered to be extensionally quantified. So we have some defaults that minimize writing extension quantification. Yeah. But if to be precise and strict, you may want to write extension quantification where you expect them. So here is another example, slightly more general, but this time you're just a list fragment. So instead of ending with a null, you end with a pointer p. Then in that case, the base case is root is equal to p, and then the length of this segment is 0. Otherwise, it is a node with r pointing to the rest of the segment. And of course, that segment will end with p, so you write a p there. Okay. And this kind of list segment is quite useful. For example, if you would like to define a circular list, then in that case, you will have a segment here. You have an initial head node here, and then you will have a segment here, and you expect the last pointer to point back to the first node. And that is defined by just saying you have a first node and then a list segment, and this thing is pointing back to the beginning of the circular linked list. And this case is a non-empty circular linked list. And an invariant that you may want to put is n greater than or equal to 1. If you put n greater than or equal to 0, it will be less informative, and then you will, of course, it's still sound, except that you has less information in your reasoning. So it's advantageous for you to put as strong an invariant as possible for your shape predicates in general. Here is another example. This time is for a tree, and this is also a height balanced tree, and we are capturing just the height here, such that if the root is null, the height is 0. If the root is non-null, we will have a left tree and a right tree, with their respective height. And then we have a formula here to tell us how to compute the height. And also, we have a balanced height property that says that the height between the two sub-tree, is either -1, 0, or 1. So it's kind of constrained to be at least, at most 1, either the same height or one different from each other. And in this case, you have also an invariant for the height. So those are the examples. And if you look at these separation formulas, there are really two parts in the formula. The first part is on the heap that describes the shapely data structures. Okay, so there's a heap part. And then there's the pure part, which essentially in our case covers size property, pointer property, and also back property. We allow backs of values to be captured in our formula. And of course, you can have also other property depending on the prover that you have, whether they are able to deal with them. You can have a list property and some other property. And the other distinguishing part in our predicate is our default parameter, the root parameter, is expected to be the beginning of the data structure. And we also expect, we have some property that expect that all nodes in this predicate that you're describing is reachable from the root pointer. Okay. So now that this introduction is made on our approach in general, let's go on to the verification and then also the proving part. So for verification, we aim for some automation as long as the users provide pre-post conditions to each method and loop. Okay, and so that's pretty standard. And then the kind of check that we perform is we check that every call site has their precondition satisfied. And also for every method, the post condition will be satisfied at the end of the method. And then the other thing about our approach to verification is we use state transitional formulas in which for every variable we will have two logical variables capturing both the initial value and the latest value or current value. And we denote that using the prime notation. So x prime is the latest value of any variable, and x is the initial value at the start of some computation, maybe at the start of the method, for example. And we use just Hoare-style verification in which we have a pre-state and then a post-state. And for verification, we're just reasoning forward. So given delta 1, the pre-state, and some code, we will compute the post-state from there. So just as a simple example, if we have a pre-state delta and then a language construct to construct a new node in the heap, then the post-state will be basically the original heap state in spatial conjunction with this new node. And the new node, as you will note, the variables here will capture the latest value. And then rest is just a special variable to denote the result of this expression. Okay. And here are some other rules in the system. This is a rule for variable. This is a rule for assignment. And then here is where we check that the shape predicate's pure invariant is sound. And we do that by taking the definition of that predicate and then subject it to a translation to a pure formula and checking that this body implies this pure formula here, so that we know that the invariant given is sound. And the main check is the check at method calls. So that's the precondition check. So at every method call, we expect the precondition to hold. And this is done by that entailment here. So the current state must imply the precondition. Okay, so that's the entailment prover that we have. And then in some sense, since separation formulas are substructural logic, this entailment prover allow us to obtain the residue or some frame condition from there for us to propagate forward from there. And then the other proving part is done over here, where after analyzing the code of the method body, we use it to check whether the post condition holds or not. And if it holds, we know that given the precondition, the method will in fact satisfy the post condition. So let me just run through a very simple example of how this verification works with the separation formulas. This is just an insertion procedure where initially X is a sorted linked list, and we're trying to insert a new node into this sorted linked list. So our precondition will be X must be a sorted linked list, and then also this Vn here will be a node with the value V. Then we expect after this insertion, the post condition will have a sorted list that is one longer, and its minimum value and maximum value may be changed, by taking into account the new node you just inserted into this sorted linked list. And here you have, of course, the normal base cases and also the recursive case in order to work. And I'll just highlight a simple fragment of this, how we do this reasoning. So we start with the initial state, the precondition, and then the variables will be, based on their latest value. So x prime and vm prime will be the latest value. X prime points to the sorted list, and vm prime is the node we're trying to insert into it. And then in the branch where we have this conditioner, we will have a few access, right? Vn dot value, which is available here, but x dot value will be this x pointing to the sorted list. We don't know whether this sorted list has a node or not. So what we do is we unfold this definition. So unfold to the right hand side of the definition that will in fact expose the node in this sorted list, and then use this. So this x bar will now be this minimum value, and then this v here will be vn dot var. So that condition will be attached from the conditioner of that then branch. Okay, so that will be the state of the system after you enter the then branch of the conditioner. Next we have a statement vn.next being assigned to x. So where is vn.next? Vn.next happens to be this location here, and that will be assigned to the latest value of x. So what will happen is this state will be updated to the latest value of x, so x prime. Then next we have a statement return the value vn as a result of this method. And in that case, vn happens to be this node here. So basically it will return this thing. But as a post condition, so of course the result will be updated to vn prime. Then as post condition, we also expect it to be a sorted list, the result to be a sorted list. So what we have to do is we take this formula and see whether you'll be able to fold to this formula. So if the entailment tells us that this thing will in fact fold into this formula, we have succeeded in proving our post condition, for this branch. So the heart of the system is really this entailment prover. And for this entailment prover, we have an antecedent, which is the current state, and also a consequent, which is the thing we are trying to prove whether the current state can imply that consequent or not. And on top of that, we capture the residue, that is any heap state that is not involved in covering this consequent. So the antecedent must subsume all nodes that are present in the consequent for this implication to hold. And then the remaining nodes that are not used will be kept in delta 3. And what the algorithm does in this entailment proving is to make sure that all nodes in the consequent is in fact subsumed by the antecedent delta 1. And when that happens, we then convert the formula to an arithmetic check to see whether the pure part holds or not. Okay? And we expect in general that the antecedent and the consequent to be given, and then the entailment prover will return the residue that has not been used by the proving. The key step in this entailment prover, basically there are just three main steps. First, we need a way to match alias node together for both the left-hand side and right-hand side, the antecedent and the consequent. So either they are both data nodes or they are both predicates. We match them up. and then we unify their respective components. Okay, so that's the matching step. Then the other step is if the left-hand side happens to be a predicate, and then the right-hand side happens to be a node, then we have to unfold the predicate in order to match up the nodes. So this is the so-called unfolding process. And then the converse is if the right-hand side happens to be a predicate, it means the consequent is a predicate, and then the left-hand side antecedent contains a data node. Both of these are alias. Then what we have to do is we have to perform a folding task, and that we make a recursive invocation to the entailment procedure. So we make a separate entailment procedure to see whether this folding can take place. Here is just a one-page summary of the rule. So the main steps, as I said, is the matching, the folding, and then the unfolding. And then these are some auxiliary rules to deal with disjunction and extension quantification. And also, when we have succeeded in this matching, I don't expect you to read this rule in this 1 minute. So just listen to me, I guess. So when we have succeeded in matching everything that is in the consequent from the antecedent, then what we do is we will have an empty heap on this side of the formula. So this is just a pure formula, and then we will make a conversion of this current state into arithmetic form, and then pass it to a normal arithmetic prover or first order prover. Okay, first order pure prover. So let me just highlight with some example, just to show you again the steps. So the key steps. So here is where we match two predicates together. So left-hand side has a predicate, and then right-hand side also has identical predicate. Then we have to match them up by unifying the parameter. So this n and n will be unified and then substituted on the right-hand side. So in the end, we are just reduced to this pure part, which will then be passed on to a normal prover, maybe like Z3. Or in our case, we make use of a Pressburger prover and also the CVC-like prover for arithmetic proving. So this is with exponential variable. We have a very special way of handling free variables. In case there was a free variable on the right-hand side, whenever there is a matching, we will in fact take this matching where n is equal to m to the left-hand side. So this is in fact quite important. For example, if you have so binding of free variables will actually move to the left-hand side. This is quite important, for example, when you have specification in which you have free variables to link your pre and post conditions. So if your current state matches the precondition, then what you want to do is to capture whatever binding that occurs for the free variables into your current state so that later on you can reason with the post condition. For unfolding, we will have a predicate on the left-hand side and then a data node on the right-hand side. And in that case, we have to unfold the predicate on the left-hand side with the body. And in this case, this predicate will have two parts, the base case and the recursive case. But the base case, because of this pure predicate, will be eliminated. So we just have the recursive case. And that will allow us to perform subsequent matching. So after this unfolding, the data nodes will in fact be matched up. And then you're left with just the rest of the linked list. In this case, they will just do a further matching and then you will complete. For folding, we will have a predicate on the right-hand side and then either a data node or a pure formula on the left-hand side. And in that case, we make a recursive invocation to this entailment procedure. So we make a separate entailment procedure in which the body of this predicate is exposed, and then we try to match up the body. And then finally, especially this is done in this way because it allows us to make instantiation of the parameter of the folded predicate. So that instantiation to the parameters of the folded predicate will appear later on the left-hand side of the formula. For recursive case, it's also similar, because when you make a recursive invocation, the base case will fail, and then the recursive case will succeed with a normal matching of the node, and then subsequently it's just another recursive invocation. And then the binding that we get from the parameters of the folded predicate may move to the left-hand side, especially if it involves free variables. If it involves bound variables, it will just stay on the right-hand side. So at the end of this entailment procedure, we will in fact do approximation to arithmetic implication. So the entailment itself eventually reduced to an entailment of pure constraint. This occurs when the consequence heap is empty after all the matching. And then each of the predicate in the final formula will be approximated by some pure constraint. I'll just highlight with an example how this approximation is done. Let's say we have a formula in which we have this spatial conjunction, and then we have two nodes. Okay? And we have variables x and y. The way we convert this to approximated pure formula is as follows. X is a pointer. Sorry, this should be a y here. Y is also a pointer. And we know that since they are data node, there's going to be non-null, so it has to be greater than 0. 0 is used to denote null. And because they are in spatial conjunction, we also add the fact that these two pointers are disjoint. So x and y are in fact different. So we add this condition in. So that will give information on the fact that these two pointers are pointing to disjoint heap. If we have a predicate, one thing that we can immediately use is, say we have this predicate x, and then which is a linked list with length n. And one thing we can immediately use is just a pure invariant. So we just can substitute the pure invariant to this position where there was a predicate. But this is kind of too weak in general. So what we do is, before we actually do that, we perform an initial unfold of the predicate. Then we convert it in that way. So after initial unfold, we will have the base case and the recursive case. The base case will be, x is a null, and then n is equal to 0. And then the recursive case is x points to a node that is non-null. And then we also know that n is greater than 0. So this can be obtained by just a single unfolding. And we only unfold once. We don't unfold more than once, because when we experiment with unfolding more than once, we just the proving just takes too long to complete. If you don't do any unfolding at all, you just use the pure formula in the conversion, then there are certain things you are unable to reason about. So the best option is just to unfold just once. Here is just some examples that we tried. So far we tried mainly small examples, but interesting examples. Things like doubly linked list, circular list, sorted list, also all kinds of sorting, insertion, deletion, barber sort, quick sort. And then various kinds of trees, binary search tree, priority queue, AVL, red-black tree, and all kinds of balance tree. And those are just the verification time when we use the omega as an underlying engine to do the arithmetic proving. Okay, so that's the basic system, and I will spend the rest of the time talking about some extension that we did to make it more expressive. We have so-called a facility where users can give multiple pre-post annotation to each method. And then we have also a facility where users can write lemmas or coercion rules relating the predicates. Okay? And I'll just show you why this is useful. Okay? Say, let's look at an example, appending two lists. This is written recursively, such that we expect that the two parameters are x and y, and we expect x to be non-null because of this initial access to the field of next. And then the precondition for this method will be, for example, one precondition will be both x and y are list segment, and they may have different length n and m, but we know that this first list segment is non-null, so this requires this precondition here. And then at the end of the method, the list will be joined up, because when we reach the last position, we will in fact assign y to x dot next, so we have a joint list that way. Okay, so this is the normal specification that you will give to this append method. So my question is, are there any other useful specification that you may want to give to this method? You know, is this specification sufficient for your need, or do you think there are more? Huh? You need more, right, in general, right? So one example will be, what happens if x and y are aliased? Now, if x and y are aliased, what it means is x and y are equal to each other, and you only really have just one list segment, not two list segments. And in that case, what is your post condition? You will be joining the last next field back to itself, right? So what you end up is you get a circular list as a result. Okay, and for this to work, you also need an auxiliary condition, where when you go to the recursive call, you use this auxiliary pre-post condition. So now you have three pre-post conditions for this method. Are there more that you would like to have? Well, what happens if you happen to use quicksort algorithm, for example, in which you recursively sort the two lists, and then towards the end, you just do a join, right? And append is a join to join the two sorted lists. Then in that case, you need another pre-post condition, but this time involving the sorted list, such that x is a sorted list, y is a sorted list. And also for this join to result in a sorted list, the maximum value from the first list must be less than the minimum value from the second list, right? And once you have that condition, then you'll get a sorted list after this join process. Okay? And since this sorted list is non-null, it's fine for x since we expect it to be non-null, but for y we will allow it to be null sometimes, so we also would like to have a possibility for y to be null, and in that case the post condition is just x itself being a sorted list. Okay? So this multiple pre-post condition is useful to add expressivity to your specification to cover more cases, more context, so that you could verify according to your context. And also, of course, multiple pre-post by itself is nothing new. I mean, intersection types that people give to types is a kind of multiple pre-post, but based on types. And then also JML allow you to give specification, and then also separate specification using the also construct. It's a kind of multiple pre-post. The only thing is in JML, they will then merge the specification together into one. So you have two pre-post specification. The underlying system will merge them into one specification by a union of their precondition and then a conjunction of their post condition based on the respective precondition. Okay, but we would like to deal with these multiple pre-posts separately and explicitly. Part of the reason is because we are using separation logic. The other reason is that we believe having multiple pre-posts is a good thing, because by having multiple specification, you are able to write smaller specification, and that is good for scalability in general. And the way we handle this is to extend our verifier and prover to deal with a set of state rather than a single state. So instead of proving with one single residue as a result, we allow our prover to return a set of residue from that proving. Okay? And that in some sense denote a non-deterministic outcome from searching for a proof for this entailment. Okay? And if we get empty set from this result, it means the entailment has failed. That means we haven't found a proof such that the entailment holds. But if we get more than one, that means there is more than one way of succeeding in this proof. And also we modify the verifier component, the Hoare-style forward verifier, to capture a set of states during the verification, code verification. Okay, so that's the set of state to support multiple prepos. The set of state is also used to support lemmas in our system, because quite often when we write predicates, some of them may indeed be related. Just looking at the predicate that we define, the linked list predicate that captures the length of the linked list, and then the sorted list predicate that captures a sorted linked list, they are in fact related in some way, because every sorted list is just an unsorted list. So you expect to be able to do this reasoning where if I have a sorted list, I should be able to convert it to a normal linked list, that is unsorted, because this is just a special case of normal linked list. So this kind of conversion rule, we call them lemmas, or we call them coercion rules. And for example, this particular conversion is necessary if you happen to verify the bubble sorting algorithm. So in bubble sort, you don't know whether something is sorted or not, depending on the flag. So if the flag, that you do the bubbling with, says that there was no exchanges, then you know the whole thing is sorted. But if the flag there say there was a change, then it means the thing is not sorted. And what you want to be able to do is to coerce the sorted list to unsorted case, so that your net result that it is unsorted. Okay. So the user can provide this kind of lemmas or coercion rule in the system, and we in fact allow, in order to match up with the way we do unfolding and folding, and which is the way we handle lemmas as well currently, is we allow you to write this kind of lemma. The left-hand side is always simple, so there's only one predicate on the left-hand side. But the right-hand side can be complex, so it can contain some other heap location other than the initial predicate or node pointed to by the root. So we allow you to write this implication. So this thing implies a complicated right-hand side. Or we allow you to write a complicated right-hand side implies a simple left-hand side. So this is the reverse implication. Or we also allow you to express equivalence. And once this is given, we in fact will prove that they are sound. So we just use our Entailment Prover to prove that it is sound by kind of co-induction. And then these lemmas will then be used by our Entailment Prover to do reasoning where necessary. Okay, and the significance of this direction is when you go from here, from this side to that side, you are allowed to do unfolding. So if you only give this rule, you're only allowed to do unfolding. But if you have this rule, you're allowed to do folding, which means if you have a predicate on the right-hand side, you can then use it in that direction. And if you have both rules, you can do both ways. Unfold left or fold right, that's fine. So that's the implications of having these lemmas. And an example of a lemma that goes both ways is as follows. We saw the list segment predicate earlier, which is a segment that may not be terminated by now. Often to reason with just this list segment itself is not adequate. So we allow you to write a slightly more general rule about list segment that allow you to break one segment into two segments. So this single segment could be broken into two segments with size I and j such that I plus j will be equal to n. Okay, and it will be joined up by this extension r here. And of course, you can go both ways. You can not only break your list segment, you can also join back your list segment. So you go this way and that way. Okay, and the termination of doing reasoning with this lemma is we have some condition on well-founded and well-formed property about the predicates, and that also applies to some extent to the lemma, allowing us to make sure that our prover always terminate when we do this entailment of separation formulas. Okay. So as an example, this kind of equivalence lemma, the way it is used is as follows. Let's say we have an entailment in which x points to a least segment, and also on the right-hand side, on the consequent, x points to another least segment. And in this case, what do we do? Should we split the left-hand side, or should we split the right-hand side? Or should we just match them up together? Maybe the two segments are of the same length, so we will match them up together. So in fact, we will do a proof search over this. One is we just match them up. So we assume they are of the right length, and then we just match them up, and then we just do this proof down this way. The other is we will unfold the left-hand side. So the left-hand side will be unfolded. And then after that, we do this matching up. So this thing will be matched up with that one. Okay. We cannot keep breaking this segment. If we keep breaking this segment, we will end up with, of course, infinite loop. So we have some way to control this such that after it unfolds, this part will not be coerced any further. And of course, the other possibility is you do a folding with a recursive invocation such that the right-hand side, is being unfolded by the lemma. And then in that case, you will match this part up. So these are the three ways to do proof search involving this segment. And hopefully one of them will succeed, and then we will have a proof of our code. And if all of them doesn't succeed, maybe there are more than one way, but usually there's only one way to do the proof, typically. Here is just some experiments we did with a set of states. So these are the earlier examples. And then we, in one case, we turn on our set of states together with multiple preposts and also lemma coercion. And here is the time it takes to do the verification. And then we also constrain the system such that we only have a single state, don't have a set of state. Then in that case, certain examples will fail because maybe those parts will not be explored by the proving. So there are some examples that will fail. Others will succeed because maybe they don't need any lemma or they don't need any search. And also the time may be slightly faster since you're not doing searching, but it's only marginally so. There's not really much difference between the one with set of states and single state. Okay. So this may be a preliminary conclusion that in general we found this mechanism, the proof search, the overhead to be low, and also critical for some examples. If you don't have this proof search, you will fail for those examples. So in this work, we have built some tools. We have built the prover itself for separation formula, which we call Sleek. And then we have a verifier for an imperative object-based language. We also have a verifier for OO language, but this is really very prototype because it was done by a student, an intern of ours over a 3-month period. So we will need more time to refine that verifier for an OO language. Okay. So just as a conclusion, just to recap the main contributions in our work is that we allow users to define predicates about data structures involving size and bag properties and with sophisticated invariance. We have shown you how to have a sound and terminating entailment proving for separation formula. And then we also look into various ways of making the verification expressive and automatic with the help of lemmas. And as future work, we are looking into inference so that we have more automation in the process. We are looking into debugging facility. So if, say, a verification fail, what we would like, we would like to have some tool that will allow the user to explore where the failure occurs. Okay? And also various extensions. We've done the extension for OO. We would like to extend it for other language feature, if possible, for verification. So that's the concluding slide, but that's not the last slide. The last slide, of course, I haven't talked about related work. There are, of course, a number of related work which we have draw inspiration from. Separation logic work from O'Hearn, Berdin, and a group. And of course, This is a kind of shape analysis as well. So we, and also, these are shape analysis work, and also related to this, of course, in terms of shape, with quantitative values like size and so on. Rugina has done some work that was published in SAS that we have followed. And also, in the case of Jia and Walker, they have an ILC system based on linear logic that has some arithmetic capability and also some way to define predicate, except the predicates, as far as I was aware, they're not allowed to be recursive, but you can define them in general. Okay, thank you. We just use a core language, just a simple core language. We have conditionals, method calls, a way to build objects.
But nothing existing. It's your own language.
It's because we are just currently we're just building prototype systems, so we just have a core language. Of course, we also did a work that, for example, translate C. We take the CL compiler and then translate it further to our core language. But that we haven't done, use it for verification purpose, but it's quite close to what we have as a core language.
So, perhaps you answered my question already. This goes back to your comment about JML. You are not saying that there is a version of JML that allows you to write assertions in separation logic.
No.
Compiler generate the code that would
No, not at this moment. No. So we haven't applied our work to a real language at this point. So at the moment, it's just based on core language.
But how large is sleep?
Sorry?
How large is your sleep engine?
How large is it? Is it in? So it's written in ML, and then as backend, we can use different provers. So the provers we have tried are like Mona, CVC Lite, also the Omega Pressburger calculator, and Isabel. How large it is? I mean, my student has a detail since he built it, but I don't think it's very large. No.
If it's small enough, I can think of it's possible to feed it into something like concise prover to do some proof search tactics. I mean, to enforce all your algorithms, and then I don't know if it's easier to connect to some external serial prover, but it seems like if you want to get proof in the end, explicit proof objects, and if your sleep engine is smaller enough, I think it's something like just to look into.
I see. Well, you see the one page involving the entailment rule. It doesn't look so big if you just look at that one page. But of course, a lot of details are hidden. But that's the essential part of the entailment proving.
When you talk about inference, are you talking about inference of procedure summaries, method summaries?
Yes, inference of pre and post condition in general. Yeah. So we have another project that does inference of both pre and post condition, and we go for disjunctive domain there. So because we find disjunct to be helpful in capturing things precisely. But in that inference engine that we had, we just deal with currently is arithmetic formulas. We don't deal with separation formulas. So it may be of interest to also see what is involved to analyze separation formula. But our inference engine at this moment. So if you gave separation formulas, like you gave the shapes that you expect in pre and post condition, then I can envision that we can use our inference engine to at least infer all the size properties from there, so that you don't have to write the size properties. So those can be inferred.
How did you look into write these properties? I mean, since you're tracking the size of the
No, we haven't looked explicitly into that. But of course, once you have the size property, it may be able to reason about termination and so on from there.
I have two questions about the lemmas that you use for the automatic
Yeah.
verifications. How many lemmas did you typically need for the kind of examples that you
showed us like lists and AVL trees and so on. And also, how do you discover the lemmas? Because if you do interactive program verification, typically you see where you get stuck and then you turn this into a lemma. But
Right.
in an automated process, that's more difficult.
Right. So at this moment, we expect the lemmas to be given. So if they are not given, then the verification will fail. Maybe from the point where it failed, the user may be inspired to come up with lemmas that will, that they can then supply back into the system for the verification to succeed. At this moment, since we are dealing with small examples, we just having a handful of lemmas, maybe 1, 2, or 3 lemmas in order to do the proving of those examples. But I expect these lemmas typically to come from the library designer. So if the designers were designing this predicate, then they will have a good idea what are the useful lemmas for those predicates and how the various predicates are related to one another. So once those are given, then our system will just prove them and then apply them automatically.